Someone joined.
No, that was the recording starting.
Oh.
Okay, so what we have to do in order to solve this with integration, I need to find the antiderivative of cosine of x dx. Anybody know what I take the derivative of to get cosine? Sine. So that means my antiderivative was sine of x, and we need to solve it at pi over 2 and 0. We always start top to bottom when we're solving integration. So the area here is going to be equal to sine of pi over 2 minus sine of 0, and I can put that straight into my calculator. Because after we take the integral, it goes straight. So that means sine solved at those 2 points. What mode should my calculator be in? Just check. Radian. Good.
I love my Casio.
Because these are radian angle measures. So if it said like 30 degrees, that would be degree mode.
Well, I took the top 10. So I need to charge it up.
So what is sine of pi over 2?
Cause
0.
1. What is sine of 0?
0.
What's 1 minus 0?
1.
So the integral from 0 to pi over 2 of cosine of x dx is equal to 1, which means the area under that curve is equal to 1.
So you can take the antiderivative of something and solve it in the points.
Correct. That is definite integration.
Wait, so how do we know it's subtraction again?
So that's instead.
We always do top minus bottom.
Okay.
That's instead of doing like graphing it, finding the area using a triangle or a trapezoid or a rectangle,
Well, that's way.
So basically,
right? That's the whole point.
if I can figure out how to do antiderivatives, we get rid of the thing that's stupid about that.
Yes. Okay, so let's do another one.
This is great. Yeah, I know. Until I have to like do part.
So now let's go from 0 to pi over 4 of secant squared x. So the first thing I need to do is I need to identify the antiderivative of secant squared x. No, that would be the derivative of secant. What is the derivative of secant squared x? You're going to want to go back to where we did trig derivatives. Antiderivative. I want antiderivative of secant squared x.
Isn't the antiderivative?
Secant squared. Oh, tan.
What do I take the derivative of that it gives me the answer secant squared x? Tangent. So tangent is the antiderivative to secant squared, so I need to solve this at tangent of pi over 4 minus tangent of 0.
What?
What is opposite?
Oh, I thought you told us.
If it was something squared. Yeah, it's not squared.
For some reason, I put pi over 4 in mine.
No, on top. And I can just put that directly into a calculator.
So that just goes right now.
And what's tangent of pi over 4? Anybody who already did it? What is it? 1. And then what's tangent of 0?
0.
So 1 minus 0 is again 1.
So
I feel like we're getting too many ones. I don't think this process actually works.
It does work, I promise. We just chose these because they have nice, pretty numbers.
Yeah, so you're gonna give us ones. that
Of
don't.
course, I'm going to give you ones that don't. So let's go ahead and do the next one.
I'm throwing my calc out the window.
Don't do it. Let's do the integral from 0 to 1/2 of 1 over the square root of 1 minus x squared dx. So now I need to figure out what gives me that as a derivative.
Oh, that's inverse.
That is an inverse function, yes. Sine inverse, yes. Everybody go to where we did the derivatives of inverse trig functions. And see that you can figure out that sine inverse derivative equals that. Make sure you can locate that in your notes.
No, that won't.
Did we all find it? We're getting there, maybe.
How many years ago did you do that? This year? Wow.
Actually, it was
that
last
this
year.
Oh, okay. I was gonna say there's no way that was this
Not
year.
doing derivatives of trig.
Yes, it was last year. It's in 2020.
Oh.
Okay. I think it was the beginning of this year. Change.
Okay, did we all find our trig inverse derivatives?
Yes.
Nope.
Okay, so now that we have identified the antiderivative of 1 over the square root of 1 minus x squared dx as sine inverse, I now need to take that sine inverse and solve it at 1/2 and at 0, and use subtraction to find my answer. So I'm going to do sine inverse of 1/2 minus sine inverse of 0. And we are okay with the decimal.
Oh, I got pi over 6.
Say that again. No, there's a sine inverse button on your calculator.
Oh.
That would be a reciprocal, and that would be cosecant. That's not what we want. But yes, Corbin, that is the exact answer. But if they give me the decimal, that's okay. If I don't say exact decimals, fine. You got pi over 6 should be, but if you do the decimal, it should be 0.5236.
How on earth did you get pi over 6?
Well, sine inverse of 1/2 is pi over 6
How do you know that?
from the unit circle.
I don't have any inverses.
Inverse simply means that sine of theta equals 1/2, and the inverse tells us what theta is. So pi over 6 is an angle. So that's how we got pi over 6 there. So we got pi over 6 minus 0, which equals pi over 6 if you did the decimal. Lauren, what is it? Okay. That would be fine if I didn't say exact value. If I said exact value, I wanted pi over 6.
Now, are these all the squiggly lines?
Are they all going to have what, honey?
The squiggly lines?
Well, if I do a decimal and I round it, then it should be a squiggly line because that's approximation. Okay, questions, concerns, or issues so far on our antiderivative integration?
Oh, I'm ready for the whole one. I don't know.
Let's do a couple more. We do only have 3 more, and then that's it. And then I'll show you one more thing, and then we're done.
So
Okay.
it's 4 more.
Yes, it is 4 more, Erin. Next one is the integral from -1 to 2 of 3x squared dx. So yesterday we talked about how to take the antiderivative of a power rule function. What happens to my exponent when I take the antiderivative? It increases by 1, so that 2 becomes a 3. And then what do I have to do with that new exponent? Divide it out. So when I simplify this, I get that my original function was x cubed, and I need to solve that at 2 and -1 to find the area under this curve.
Why is it a straight line over there?
Because I'm solving it at.
I got it. Just wait till the-
That's it. So 2 cubed is 8. Minus, what's -1 cubed? -1. 8 minus a -1 becomes 8 plus 1, which is 9.
Alright, this might be dumb, but where did you get the 2?
That was my integration interval. How do we feel about this? Good? Not terrible? Okay, so let's do another one. Anybody have an idea of how I can find the antiderivative of 8?
X to the 0 is right.
Okay, so we can recognize that 8 is the same as 8x to the 0, which means it's still a power rule function. So I still have to increase that exponent by 1 and then divide the new exponent out. So when I increase 0 by 1, it becomes 1. I divide that 1 out and I just get 8x. And then I solve it at my interval values. And I know that works because if I take the derivative of 8x, the x falls off and it's just an 8. So questions, concerns, or issues with that one? I'm easing you into antiderivatives. So your homework, I don't think I made much harder than this. And then we're going to keep going on Monday, okay? So we'll get a little more complicated. We have 2 more examples, and then we are 100% done. Next integral is going to go from 1 to 4 of negative x to the negative 2 power dx. And I would like to integrate it from 1 to 4. Walkle, what am I going to do to find the antiderivative here? So that becomes a negative 1 exponent, and then what? Divide that exponent out, which means my negatives cancel, and I just have x to the negative 1, which if you wanted to, you could just put as 1 over x, because that's the same thing. And then I solve it at my integral domain. So when I plug those in, I get 1 over 4 minus 1, which equals what? Negative 3/4. Well, 1 is the same as 4 over 4. 1 minus 4 is negative 3.
I put 3 instead of 4.
How do we feel about that? Okay. So the last thing I'm going to show you is really not difficult. It's just kind of another variation of integration. And this is called our average or mean value. And this just says if the function f is integrable, I don't like that, that's a terrible word, on the closed interval a to b, its average or mean value on the interval, again, a to b, is denoted as the AV of f, which just means average of f. And this is equal to 1 over b minus a times the integral from a to b of f of x dx. So if I want to find the average value of an integral, I take that integral and I multiply it by 1 over b minus a, where b is my top interval value and a is my bottom interval value. Okay, so we'll write it and then I will do an example.
What's the AV of that?
Average of f. So for this one, we're going to use a nice, really easy function. So we're going to use one that we've already done. And in here, I'm going to have the integral from negative 1 to 2 of 3x squared dx. And I would like to find the average.
Average what?
Value on that interval. So I'm still going to have to solve the integral here, right? So I still have to find the antiderivative. I still have to solve it at 2 and negative 1. I know the antiderivative of 3x squared comes out to be what? X cubed. So I take x cubed, I solve it at 2 and negative 1, and then I take that answer and I multiply it by 1 over 2 minus negative 1. So top interval minus bottom interval. This then becomes 1/3 times, well, 2 cubed minus negative 1 cubed I know inside 2 cubed is 8. -1 cubed is -1. 8 minus -1 becomes 9, which means my average value on that integral is 3. So we just do the integration like normal, and then multiply it by 1 over b minus a for my integral values.
Why couldn't you just find the average?
It's not always that easy.
Why?
Because I could have some below and some above, and then it's a little bit different.
How can you have something that's harder to find the average of? Like you can just plug in the 2 points and add them together divided by 2.
In theory, yes. For something like this, yes. But when I'm finding the average maybe of the area between 2 graphs, it's a little bit different. So this is a step into it. So yes, for something like this that's straightforward, you could absolutely do that. But not later on. Okay, so we are going to stop here. The rest is just homework time for you. I do suggest maybe that you try and work with a partner. And then Monday we're going to do a little bit, I don't know, more with anti-differentiation.
I don't like that.
You don't like it? It's a very, very small piece.